Okay, folks, we are on section 3.4, derivatives as a rate of change. This section looks at applications of the derivative by focusing on the interpretation of the derivative as the rate of change of a function. These applications include acceleration, velocity in physics, population growth rates in biology, and marginal functions in economics. So the amount of change, one application for derivatives is to estimate an unknown value of a function at a point by using a known value of a function at some given point together with its rate of change at the point. Now, having said that, I have a picture down below as well, but picture that you have a point such as, it doesn't matter if I would say 2, 5, something like that. And then I knew what f prime of 2 was, which is the slope, right, at that point. So maybe f prime of 2 was, let's say, 3, right? So what we can do, picture this, that we can put on a tangent line, right? And here is f. This is f. So we have f prime of 2 is 3. So we know in this neighborhood that of the 0.25, we know that the slope is 3. So we can write an equation for that brown line, and that would be y minus 5 is equal to 3 times the quantity x minus 2. And maybe, just maybe, you had a point, I don't know, we'll get really close to 2, and say there was a point, this is 2.1, and then some kind of y value, but we really can't figure it out right now. If we have that line, we can figure out a really close approximation. It's only different. It's a very small difference between the line and the function itself. So if I wanted to approximate the y value here, then I could do that using a line. Very convenient to do this. So what I would call this is a linear approximation of the function. But remember, this is for values that are very close to a known value, this 2,5. And at that point, you also know the slope. Okay, so the first example here that we have, we're talking about the things that we'll discuss. The amount of change over an interval is just f of a plus h minus f of a. So that, and then the average rate of change of the function over the interval. So that was the amount of change in f of x. Now we have the average rate of change, which is going to be this next one. And then after that, we have the instantaneous rate of change. Now, the instantaneous rate of change, you have to remember, has that limit with it, right? So that's what makes it different from a secant line, where the slope of the tangent line is the one with the limit. The slope of the secant line is the amount of change. It's like average rate of change, okay? For small enough values of h, then f prime of a is equal to the average slope. All right, so if we keep that h pretty small, or relatively small considering other things at bay, like a huge population or something like that, then we could have 2 might be a small change in h, or an h value, that there would be a small change that we could deal with. But for small enough values of h, if we're talking about population that's in the 100,000, that's not anything. So here we go, the first one. So what I wanted to show you is that if you look, we have this point slope form up here, right above that. So that's really all you're dealing with here. Your h value, though, if you see, is x minus x1. Okay, it's the difference in x's that we're talking about. But it's going to be constant. We're going to accept it at 0.2 for this first one, because we are looking at finding f of 3.2. We want to estimate that. So we have f of 3, that's 2, and we have f prime of 3, that's 5. So you can see in the equation, we can substitute in. So we get f of 3.2 then is approximately equal to 2 plus f prime of 3 is 5 times 0.2. Okay, so we get 2. It's equal to 2 plus 1. So it's equal to 3. So our approximation here, f of 3.2, f of 3.2 is approximately equal to 3 using this method. Like I said, we're approximating. There's another picture there. If I'm looking at 3.2 and I'm just above, it might be an overestimate, but we can use that linear equation to find it. So here we have f of 10.1, but we're going to start at f of 10. So f of 10 in this case is -5, plus f prime is 6. F prime of 10 is 6, and then we have times 0.1. So we have all our information in, and now we just multiply and simplify. So we get -5 plus 0.6, so I get -4.4. That's our f of 10.1. Okay. All right. So linear approximations are kind of nice, especially if you have a complicated function and you just want a real quick estimate. All right, so this one, a population of a city is tripling every 5 years. If its current population is 10,000, what will be its approximate population 2 years from now? So you might think 2 is a little big, but it's actually okay. It's just an approximation. So in this case, we know that p of 0, consider that p of 0 is 10, and that's time t equals 0. But p of 5 is going to be tripling every 5 years. So it's been 5 years since p of 0, right? So we're going to say that that's 30 at time t equal 5, right? And now we do have an average rate of change. We know p prime of 0 is approximately p of 5, the average rate of change, right, between 2 points, minus p of 0 over 5 minus 0. And so you're going to get 30 minus 10 over 5. So what do we get for a value there? We get 4. So we get 4, 20 over 5. So we get p prime of 0 is approximately 4. Okay? So now that we have that, now we're going to come back over here, and we're going to get our approximation for 2 years from now. Okay, so p of 0 plus 2, there's my initial, is equal to p of 0, p of 2 then, is equal to p of 0, which is 10, plus p prime of 0 is 4 times 2. So it looks like what we have is 18, right? So p of 2 is approximately 18. So what is 18? It means 18,000, right? Because 10 was 10,000, right? At times t equals 0. So the current population, in 2 years, the population would be 18,000. So in 2 years, approximately 18,000. Let's put dollar signs on that. Using the same method of approximation. Then we have another one. The current population of mosquito colony is known to be 3,000. That is, p of 0 is equal to 3,000 if p prime of 0 is equal to 100. Estimate the size of the population in 3 days, where it is measured in days, where t is measured in days. So time t equals 0 is the initial, and t equals 3. We don't know what p of 3 is, right? So we do know p of 0 is equal to 3,000, okay? And then we know p prime of 0 is equal to 100. I know it says it right up there, but I'm just going to put it in. And then the time span that's going to change is going to be our 8h, 3 days, right? So I'm looking at P of 0 plus 3. H is going to be our 3. So we get, that's approximately goes to P of 0. P of 0 is 3,000. Plus P prime of 0 is 100 times 3. Okay, so in 3 days, this is our approximation. So P of 3 is approximately 3,300. And that would be 3,300 mosquitoes, right? Ugh. In just 3 days. So it says, estimate the size of the population of mosquitoes in 3 days, where T is measured in days. So in 3 days, the mosquito population, the mosquito population will be about 3,300. Okay. I don't know if we have much more time. I think I wanted to do some of this here. Velocity, speed, and acceleration of the object here. So I think I'm going to have to stop before this video gets too long here. I know the last one's going to be a little bit shorter, but I'm going to stop and then come back and do the final video.